In this module, we will start our discussion of function of many variables moving towards multivariable calculus. So our key interest here is to understand the concept of a partial derivative, which is extremely important across many aspects of physical chemistry and physics. So what is a function in many variables? To understand this, first let's look at what does it mean to have a function in one variable. For instance, we could be looking at a problem where we have temperature as a function of the time of the year. So this could be in unit of months. So time is small t and temperature is as a function of this small t. So if you are in, let's say, Washington, DC, and this is January, and then this is a periodic function, but let's say we start from January to December. So we expect kind of this function to look something like it's cold, and then it rises, and then it again kind of goes back. But now you might ask, well, this is true for Washington, DC. But if I went to Mount Everest, clearly this won't be true. At Mount Everest, we would expect this function to be looking something like, it might have similar behavior, but it will be much lower, right? It will rise up again in the summer, but fall down to a much smaller value. So this would be at the top of Mount Everest. So we already have, so what you're seeing here is that this function does not depend only on time. It might depend on other variables. For example, we could quantify DC and Everest, the difference between them, by introducing a second variable, the elevation, right? We could say DC is at sea level and Everest is at, well, Everest level around 29,000 feet or 8,940 meters above sea level. So we could think of this function. So temperature as a function of time was in one dimension, and we can think of it now as temperature as a function of time and elevation, which is now a function of two dimensions. In top of elevation, we could add more variables. We could have added temperature as a function of time, elevation, latitude, longitude. We could add as many variables as possible. So this brings us to the general notion of a function of many variables. So far we have been looking at f of x, but now we are going to think of functions such as f of x comma y comma z, and there could be more and more variables. Why does it matter in chemistry? Well, a classic example is the ideal gas law. In ideal gas law, we think of pressure is equal to nRT by V. So if you're willing to hold the temperature constant, then you could think as pressure. If T is equal to constant, then you could think as pressure as a function of V. But if T is also variable, then this becomes a function of two variables, pressure as a function of volume and temperature. And you might have something going on where N itself is changing, the number of moles of gases itself is changing. Then it would be a function of three variables. So these things are extremely common in chemistry. And in fact, in subjects such as thermodynamics, your command of the subject is strongly correlated to how comfortable you are with the notion of functions of many variables. So now that we have introduced the concept of a function in many variables, let's see what does it mean to differentiate a function of many variables. Again, we will start with what does it mean to differentiate a function of one variable. So for a function of one variable, you can recall that we defined the derivative f prime of x, which was also denoted as df by dx, is equal to limit as delta x tends to 0 of f of x plus delta x minus f of x divided by delta x. So geometrically, what did this mean? Geometrically, what this meant was that we had a function of x and x. Let's say this function looked something like this. We went to some point x, we went to some point x plus delta x. We looked at the difference of the function in between these 2 points, and then let this delta x shrink to 0. And then as this shrinks, as delta x tends to 0, this thing in blue also becomes smaller, hopefully, and then we get a ratio of these two quantities, like the derivative. So we could do so what does it mean? It means the change in the function with respect to small changes in x. Change in the function f of x with respect to what is called infinitesimal changes in the variable x. But now we have two variables at a time. So how do we do this? Well, the idea is quite intuitive. We can keep, if we have a function of two variables, f of x comma y, we can again define what is called a partial derivative. I will mark it in blue because it is a new concept here. We can have a partial derivative which is defined as partial f with respect to partial x. Anytime you see a partial, it means that there are other variables that are being held constant. And these variables that are being held constant are denoted with a small subscript y in the bottom. If you have a partial derivative where you do not denote this subscript y in the bottom, then that is nonsensical. It means nothing. What does it mean? What was held constant? This is incomplete. So partial derivative is complete only if you specify what was being held constant. So in this case, so this tells you that it is a function of two variables. You could have had y comma z, that would have implied it's a function of three variables. So this is a first order partial derivative, just like we had a first order derivative over there. I will call it first order PD, partial derivative, as short form. This is defined similar to the function above, limit as delta x tends to 0 of f of x plus delta x minus f of x, and I'm going to come back and finish the brackets in a little bit, divided by delta x, but now we have a y to worry about. So what we do is to keep that y constant. The y is not changed, we only look at certain values of x and change it. So you could imagine that in this plot that I drew over here, there is a y-axis that extends orthogonally on the left side, and all of this is being done for one particular plane in the y-axis. You could do all of this in one particular plane of the y-axis, which is a bit different from what you considered over there. And then it would be then it would be at a second value of the constant y. So this is how it is done. We will work through some examples of this and see how to actually compute it. But as it happens in a lot of calculus, of one variables, you end up not calculating these things by using this formula of the limit, but you kind of remember a couple of things and then you manipulate it around by using chain rule and product rule and things like that. So just to complete, similarly, you could have calculated partial of f with respect to y by keeping x constant, and now it would be limit delta y tends to 0, f of x is now kept constant, y plus delta y minus f x comma y divided by delta y. So these are our definitions of the partial derivatives. So we can extend this notion to second derivatives by differentiating upon the first order derivatives. So the second order derivatives will be, by the way, another notation for this that you will see once in a while is fx, f subscript x or f subscript y. But typically, at least I prefer to use partial f over partial x just to avoid ambiguity, because f subscript x could also mean components, but you might see it in a few books. So now second order derivative is, the first one would be to take the first order derivative with respect to x of, not of the function f, but of partial f by partial x. So here we calculated partial f by partial x at constant y, and we could differentiate that. So let's understand what is this thing first. Actually, let's take a step back. So we calculated partial f by partial x at constant y for a function f of xy. We can think of this as another function g of x comma y. So just because we have differentiated with respect to x does not mean we have completely gotten rid of the variable x. It is still going to be there. So now we could do the same manipulations on g. We could calculate partial g with respect to x at constant y, right? So, but we know what is g. This g is not just any ordinary function. This g was obtained by doing a partial derivative on f to begin with. So this thing will now be partial by partial x, and it gets a bit messy while writing it, but it's not very complicated, of something with keeping y constant. And what is that something? That something itself is partial f by partial x at constant y. So in thermodynamics, typically we end up working with functions of 3 variables. That there are profound reasons for why we end up working with 3 variables. Why do we not typically need 4 variables? That is connected to the concept of an equation of state, and you will be studying it in physical chemistry. Similarly, in other physical problems also, you end up using 2 or 3 variables or maybe 4 variables for a given physical problem at hand, but the number of variables that you need is context dependent. It will change from subject to subject. So this is our first order partial derivative with respect to g, but it is actually a second order partial derivative with respect to x, with respect to f, because we have 2 delta. So this delta or nabla symbol. So this thing is called delta or nabla, if I got it right. So this thing has a shortcut. It can be written as so. In other words, we have second derivative of x with respect to x, double partial derivative with respect to x, which is partial square f by partial x square. And here I'm focusing on functions of 2 variables. If I had functions of more than 2 variables, then I would have to specify what was being held constant. So in this case, since I want to have your first introduction to this concept, I'm going to avoid that and just focus on function of 2 variables, where it's obvious what is being held constant because there are only 2 variables. So if I'm differentiating with respect to x, it is y that is being held constant. And same for differentiating with respect to y, then it is x that is being held constant. So this would be partial y squared. So what does this mean? This means derivative with respect to y after taking one partial derivative. And this is derivative with respect to x after taking one partial derivative with respect to x. We could have cross terms, and those are quite interesting. We could have fxy, which would be partial square f, partial x, partial y. So this is derivative with respect to x of partial f by partial y, and we have fyx, which is derivative with respect to y of for many very well behaved functions. There is a theorem which is, I believe, called, let's see if I get the spelling right, Clairaut's, and the pronunciation, I have no claims to being right, Clairaut's theorem, which says that under very generic conditions, fxy will be equal to fyx. And that is super interesting. I will get some homework problems on that in the associated modules, but you can go and check it. Basically, if the first derivatives, partial f by partial y and partial f by partial x, are continuous and differentiable and some other nice properties, which is true for many generic physical functions, this happens to be true. So in physics, when describing practical systems, most of the time this will be true. Not always. If you have discontinuities, then it will not be true. And you will see examples of that too. So this sums up our definition of partial derivatives. Let's look at a few examples on how they are actually calculated, and that will give you some more intuition. Let's say our function of x comma y is 3xy squared plus x plus 2y squared. In this case, let's go and calculate some of the partial derivatives. Let's say we first calculate partial f by partial x, keeping y constant. What does that mean? This y term over here, we just treat it as a constant. We do nothing to it. So what does that mean? That would be y squared partial with respect to x of 3x, because it's a constant, so it comes up front. plus partial with respect to x of x, and this third term is just going to be 0 because y is a constant. So when differentiating with respect to x, there is nothing that is changing over here. So what does it mean for us? This becomes 3y squared plus 1. We can also calculate partial with respect to y, keeping x constant. Now the first term will give us 3x partial with respect to y. So you got to be careful in these things and not run through it too quickly, at least in the first few times you're doing it. With respect to y, x is a constant, so that's just going to be 0. With respect to y, 2y squared will give us 4y, but let's write it down just to be clear. Partial y of y squared. So you will notice that in these things, I did not specify what is being kept constant because now there is only one variable in the system. So this partial derivative is the same as actual derivative that we saw earlier for functions of one variable. Once we have only one variable function in the function that we are operating upon. So then this becomes 3x multiplied by 2y or 6xy plus 4y. Let's go and check our claim that we made earlier that for most well-behaved functions, the order of the double derivative does not matter. So let's compute partial square f by partial x partial y. What will that mean? That will mean the derivative with respect to x of this quantity. What's that going to be? That's going to be 6y, and this is a constant when differentiating with respect to x, so this is just 6y. While partial square f by partial y partial x is going to be coming from this one over here, differentiating it with respect to y in this case. So the first term when differentiated with respect to y gives us a 6y, and the second term is a constant, it gives us 0. So lo and behold, they are actually the same. We got the same thing. And this is not true for just this random function that we considered. This is true for a large number of well-behaved generic functions. In general, if you see just algebraic terms or even exponential terms, it's going to be true. The problem, or trigonometric terms, the problem happens when you have things such as the delta function or functions that are suddenly changing. You specify something such as f of x comma y is equal to this value if x is less than or equal to 1, and some other value if x is more than 1, and you might have a discontinuity at x is equal to 1. Domains, with such split domains, you might run into problem. But if the function is defined on the same domain and you have just algebraic things or trigonometric or exponential, then most likely these two things will always be the same. Let's look at one more example closer to chemistry before we finish this module. Let's consider the ideal gas law for fixed number of moles. So let's say for 1 mole, let's say. So let's consider pressure as a function of volume and temperature. This is going to P Pt is equal to RT by V. So now we can calculate partial derivative of pressure with respect to volume, keeping T constant. And again, we have specified it's a function of only 2 variables. So here, if you remove the T, you're not doing sin. It's okay because we have specified right before it that it's a function only of 2 variables. So now you can see with respect to volume, it will be RT partial with respect to volume of 1 by V, which is minus RT by V squared. So the change in pressure with respect to volume, keeping temperature constant, is proportional to 1 over squared of volume. And that's really interesting, I would say. Similarly, we can calculate partial of pressure with respect to temperature. That will be R over V. You can go back and calculate the thing that I mentioned earlier, partials. If we differentiate this one with respect to temperature, we get minus R over V squared. And if we differentiate in the other order, this one with respect to volume, we again get minus R over V squared. So once again, they are same. This is again because you had only algebraic terms over here. You can go and calculate further partial second order derivatives. You can calculate partial square P by partial V square. That in this case it will be partial by partial V of minus RT by V square which is 2RT by V cube, and similarly partial square P by partial T square will be coming from this term. There is no temperature over here, so this will be 0. So that finishes our introduction to the concept of partial derivatives. Next module, we will talk about the concept of the total derivative or the total differential, which is you say, okay, I understand that there is the partial change when one variable is changed, which is this much. There is partial change, which another variable is changed, which is something else. Can I have a measure of what is the total change if both of these variables were changed somehow at the same time? And that's called the total derivative. So that we will do in the next module. Thank you very much.